Okay. Was everybody able to get onto our Slack channel? Okay. And set up notifications or whatever for it. Make sure you pay attention to that, because there might be some situations where kind of last minute I switch class to a Zoom class or something like that. Hopefully that's not a very often thing, but I know some of you have already knew. But so my wife has stage 4 bladder cancer, so sometimes we're doing like last minute doctor's runs and stuff like that I have to get her there and have to do class from like the car. But most of the time we'll be here. Just make sure you're paying attention to Slack so you don't like show up to an empty classroom or something like that. All right. So let's see, at the end of class last time, we had just looked at the Linux assembly of Hello World, right? Gone through and kind of saw the low level language. Let's see, we were kind of talking about, here's the different ways of classifying languages. Looked at low level, high level. So I think we wrote a Hello World program like in C. Saw that it was, just really one line of code outside of the couple of fluff wrapper stuff in C to make the program work. And then we went and looked at Hello World, and I'll bring that up again real quick. Hello World, Linux assembly. This guy, and saw that all this stuff here is actually heavily leveraging the operating system, the Linux operating system. So it's taking advantage of these hundreds and hundreds of lines of code of stuff that lives inside of this syswrite system call. So even though this doesn't look very friendly to a human being, this is actually still using a power tool. If we rolled back to the very early days, before operating systems had all these system things and stuff, we would have had to write all this by ourselves. So Hello World might have been like a 1,000-line program to put Hello World to the screen, and most of you would have changed majors, right? Although back then, so we think, we really think about it, and this is kind of picking up where we left off last time, because I think I was mentioning something near the end of class about, when you play like these latest, greatest video games and stuff, you see all the fancy graphics and the controls and things like that. You think, oh, that would be really, really difficult to write. We have such advanced tools now for software engineering that, every hard program is made up of a bunch of easy parts. And really, there's nothing that special about a big video game like that, or even an operating system. There might be lots and lots and lots of lines of code, because when you think about, like I think I mentioned last time, like Windows, I think somebody said Windows XP was the first one you remembered, right? But like now, Windows 11, has everybody pretty much adopted that, or some of you still sitting on Windows 10? But I sit on Windows 10 because I do a lot of virtual reality stuff, and Windows 11 is, they claim they fixed the problem, but I would say it's still a little sketch how it supports VR. Out of curiosity, how many of you have done virtual reality stuff before? Okay. If you're interested in trying it out, send me a message on Slack or something like that. We do a lot of virtual reality development here in the department. And we have a whole bunch of headsets. So we have a bunch of Quest 2 headsets, and we have PC VR stuff as well as mobile VR stuff. And I have a grant from Meta, whether you like Facebook or not. They gave us $250,000 to do VR research and development. So we have a lot of kind of cool equipment that you might not necessarily be able to just buy on the shelves and stuff. So if you're interested in playing around with cool tech, take advantage of it. I can certainly get you involved in at least trying out those things. But even if you just want to play video games on them, we have the headsets. And then also the same thing goes for like our maker space. Most of you have probably seen that over in the first floor of the plaster building. The zillion 3D printers that are down there. We have another like 80 upstairs there. That's free to use for computer science majors or anybody taking our classes. So free plastic, go down, print off your baby Yodas. That's what everybody does first. When they work with 3D printers, you always print off some like Batman or something like that. Then you actually start trying to invent real things. Plus, we have a really cool 3D scanner we just got that's not available in the United States, that we got from a research and development place in China that's shockingly good at 3D scanning. Because we have another one that was like $8,000 that sucks. It's just terrible. Like, why have it? But this other one's pretty good. So if you have like a, I brought in a thing from my shower rod that had broken at my house, and it's some old piece that you wouldn't be able to go and buy. You would just have to replace the thing that probably would have required me to replace the shower door to get the holes in the right place. But I brought it in, we 3D scanned it in probably 5 minutes, printed it in about an hour. Now I have a carbon fiber version of that. That's never going to break again. The glass will break first, but lots of cool stuff. So I encourage you to take advantage of that, because students typically do not. And we want people down there using the makerspace. Professor Liao, I don't think any of you have him yet, but he's the Chinese guy you maybe see running around the department. He runs our makerspace. He was a former grad student here, and he's working on his PhD, and he teaches undergrad classes as well. But 3/4 of his job is to do makerspace stuff. So feel free to go and learn about the stuff, even if you've never used it before. All right, so here's my pitch. Long way around. Make sure you check Slack is the punchline there. Oh, I also put up just the other day on Slack, on general, I think yesterday, the job fairs that are coming up. So there's going to be companies there. I have the dates and where they are located. There'll be companies there that will potentially hire computer science interns that we've worked with as well. A lot of times the students will do their internship after like their sophomore year, but there's no reason why you can't look for a beginning internship after your freshman year this coming summer or something like that. So certainly go and they're in the hall outside of the chapel on those dates, and it says which companies are here that are related to computer science. So swing by at the very least. All right, so we had talked about high level versus low level versus machine level code. So this would be considered low level. Low level has a one-to-one relationship with the CPU. Whereas a high level language like C, C++, Java, C#, pretty much any language you've heard of is a high level language. You write one line of code, it's going to translate into a bunch of lines like this. That ultimately then get turned into zeros and ones. All right, so zeros and ones are not friendly for human beings. We could maybe do this in short bursts, but we rather use high level languages because we like power tools. Okay, so we're going to mostly focus on high level languages, although in the 325 class that you'll have next semester, you will be working with assembly like this, but the things you're writing are going to be very simple things. If you roll back to, let's call it the mid 1980s or something like that, or early 1980s, the computer programs that were out are not like the programs we have out today. The languages were not strong enough tools to allow a human being to solve some of the very complex problems we have today. So we've evolved to these more powerful languages that allow us to solve harder problems, let's say, but we're still way short of being able to solve problems that as human beings we maybe take for granted. Like I used the example last time of like walking. We're so good at solving problems that we have trouble articulating how we solve it. And that's the skill we really have to have in order to tell a computer what to do. So at the end of the day, if you say, oh, can I write a program for something? You start off by asking yourself, is it even going to be possible for a human being to articulate all the steps of that? Whether you can do it or not, maybe you're not practiced enough yet, but is it even possible? So like I brought up walking as an example, it doesn't matter how good you've gotten at, breaking problems down to tiny little pieces. Chances are you're never going to be able to fully describe each and every little step that is the recipe of walking, right? That seems like an incredibly complex thing. Yet the antithesis to that is, as human beings, it's not even worth our full attention. We're texting and stuff while we're doing it. So make sure you manage your expectations of what you'll be able to write software for. And I think I mentioned last time, that's where some of these cool things like artificial intelligence and machine learning starts coming in to kind of solve those problems, potentially solve those problems that a human being can do, but can't articulate the steps for. So if you want to connect a few of those dots, maybe creating a robot, which some of these exist, robots that are fully articulated that you've seen on, Travel Channel or, Discovery Channel or something like that, where they can walk up and down stairs and, they walk around like people. Chances are the walking aspect of that, and maybe a lot of the aspects of that robot, are built on top of artificial intelligence and neural networks, where somebody didn't sit there and program how to make the robot walk. Instead, they sat there and let the robot fall over a zillion times until it finally figured out how to stay up. And that became its walking engine, pretty similar to how people, learn how to walk, right? You're a little baby. First of all, you're sitting there doing nothing. Then you start crawling. Then you sort of stand and fall. And then you stay on your feet. And next thing you know, you're mobile all over the place, right? Kind of treating things like that. So that's not programming, but that requires computer programming to build the tool to allow us to train a neural network. But now we have power tools for that as well. All right, so a lot of cool stuff going on with technology that we can take advantage of as computer programmers, but just make sure like I said, you can pass this through your own filter. If you don't think it would be possible for a human being to describe every little step on how to solve a problem, chances are you won't be able to write a program to tell a computer how to do it. Okay? All right. So we'll run into slides that talk about some of these different things. Wrote that. All right, so you saw this last time. I'll go ahead and pop open my, here it is here. So I have this statement here that, am I even in the right class? Yes, that's the master one. Okay. So I make this statement that all programs begin and end with main. All right. Now, the reason for that, and I think I have a picture here for it, but if I don't, I'll create a slide for it. Yeah, I'm going to just create a slide for it. We might bump into it later on, but rather than wasting time. One thing that's helpful for us is to consider where our modern programming languages came from. Because there's a lot, whether you've written any software before or not, there's programming languages that you've maybe heard of. So how many of you have heard of C? C++, Java, Python, JavaScript, Scheme, probably not, although I think I mentioned it in class last time. But you kind of get a C#, .NET stuff. So, there's all these languages that you've heard of. Now, all those languages I just mentioned, every single one of them is a derivative. It came from the C programming language. So kind of in the late 60s, a programming language, actually a little earlier than that, but let's just call it late 60s, a programming language came out called C. All right. And C was a language originally created for writing operating systems. So kind of connecting the dots, what we've been talking about here. So, and by the way, like my exams, I mean, this stuff is important to connect some dots, but I'm not going to like test you in my class on like, when did C come out or something like that. This class is primarily testing you over programming knowledge and things like that. And before exams, I always go through the slides and I kind of point out, this is a high priority thing. This is something I probably wouldn't ask on an exam. All my exams are 10 questions, short answer, or writing code, no multiple choice or true false stuff on my exams. And I go through the slides and tell you which things don't focus on, but other things that you can expect to be on the exam. So in any case, and we'll pigeonhole some of these things because I had this slide back here where I said it's helpful when you've been programming, you already have computer programming as a skill set. It's helpful for us to look at a language and say, okay, what kind of language are you? Are you a high level, low level, or machine language? Well, most of them we're going to use are high level languages. Are you a compiled or an interpreted language? And we'll talk about that a little bit more, but that does give us some information. And that's very related to this next thing about loosely typed versus strongly typed. Okay. So just giving you the high level, maybe we'll talk about it in more detail later. A compiled language turns into machine code before you run the program. And interpreted language turns into machine code, let's say, once you start running the program. So you can think of it like if you're listening to some foreign leader give a speech in their language, and the news station you're on is translating it in real time. You're kind of on a 2-second delay, something like that. That would be an interpreted language. Where a compiled language is, your news station gets an already translated script of what was said, and they have the English version, they just read it. Now you're getting it in real time without the delay. So we would say something like compiled languages are often faster than interpreted languages. And a good example of compiled languages are going to be like C, C++, Java, C#, Swift. How many of you have heard of Swift? Okay, Swift is Apple's more modern language. The language they had before was called a language called Objective-C. You're going to see that on our chart here in a second. But all those languages are compiled languages. How many of you have heard of a language called Python? Python's an interpreted language. JavaScript is an interpreted language. Okay, there's nothing wrong with those languages, and our computers are so fast today that frankly 99% of the time, higher than that, let's call it 99.9% of the time, it doesn't matter whether it's a compiled or an interpreted language. Maybe the main place for us, the main two places that we would expect that program to have been written in a compiled language would be video games and operating systems. Things that really need to be as fast as possible. Okay, but business applications, I mean, your computer is so capable of running something like Microsoft Word, right? That those could be written in interpreted languages, and as a human, you're never going to know. It's going to feel just as fast as if it was written in a compiled language. All right. So whether it's a compiled or interpreted language, often, in fact, I think in pretty much every case I can think of, is linked to this next one, loosely typed versus strongly typed. And this is related, I think last time I talked about how do human beings solve problems. We remember things, we ask questions, and we use repetition, okay? And I said that every single programming language will have facilities for those three things, right? So that means every single programming language is going to have a facility for remembering stuff. And that facility in most languages is called variables. Okay, we have name value pairs, a named piece of memory that we can put a value in. Compiled languages typically use strongly typed variables, which means that when you create a bucket to hold a value, you have to tell the language what kind of value you're going to store in there at the time you create that bucket. Interpreted languages are typically loosely typed, where you can create a bucket and you don't have to tell the language what kind of thing you're going to hold in there. It'll figure it out when you throw the first thing in, okay? But you can also change the thing that's in there, which from a programming perspective doesn't actually make a whole lot of sense. And that'll become clearer once we get into this. But if we think about real life, typically we operate under maybe a loosely typed model, because our version of a variable might be, let's say you have a bunch of tax documents that you're going to keep under the bed. Well, you go over to Target and you get one of those Tupperware containers, right? And you put the tax documents in it, you slide it under the bed, and that's your tax document bucket. Okay, that's like a variable called my tax documents. Well, if later on you decide, okay, well, I don't keep very good records anyway, so you're going to dump those out and put shoes into that same container. You could, right? Why go buy a new container when your shoes might fit in that one? Make sense? That's a loosely typed language where you can have a variable that can hold whatever you want to put in there. Chances are, though, when we name our, like in that case, I said this bucket is called my tax documents, you probably would not expect to find shoes inside of a box labeled my tax documents. So if you just moved and everything's in boxes and you're going to unpack and you're looking for your tax documents and you come across a box that's labeled, or you're looking for your shoes and you come across a box that's labeled my tax documents, you might not look in there, right? Because you assume that's not shoes, when in real life, we very well might have put shoes in there. Probably should relabel it, but. So loosely typed languages, even though they don't make you define what kind of thing goes in there, what you name that variable really should accurately describe what you intend to put in there. Where a strongly typed language, that would say when you go to Target and you buy that first container for tax documents, you strictly label it as tax documents, and the only thing that's ever allowed to be stored in there is tax documents. If you decide to switch and you want to store something else in the same location where that was, you got to pitch that box and go get a new one to store your shoes. All right. I would make the argument that even though that's less kind of human flexible, it's actually the more compatible way with, I would say, good programming practice. All right. And it's actually the reason why I use as our first language in here, also because it's going to be at the top of the thing, we're going to be using C in this class initially, which I promise you is not the friendliest language you can learn first. It's not bad. And that's kind of the reason I like to start with it, but it kind of gives you the rationale of why we have more modern languages that came from C. And we will kind of evolve to C++, and then you'll see next semester we look at Java. It's the same language. All these languages are the same because they all came from C. Go ahead.
So like strongly typed means you can't reassign things. Once it's assigned, you can't change the value, and loosely typed, then you can reassign the value.
Yeah, well, any sort of variable, you can change the value. You just can't change the type of value that was stored there. Yeah, if you create a variable in a strongly typed language that's defined as an int value, that means that's only capable of holding an int. You can't put like a Boolean in there. Yeah, you can't change the kind of animal you put in there. But if you put a 5 in there initially, you can change it to a 9.
Okay.
Yeah, as long as you stay within the same kind of value. Right? And we'll see tons and tons and tons of examples of this. So I'm giving you very broad strokes of these things right now. Okay. But compiled languages tend to be strongly typed. Interpreted languages tend to be loosely typed. Python, which is commonly used as a first programming language. I think JavaScript is sometimes used in like high schools and stuff. Both of those languages are loosely typed. And one of the things you will often maybe see online or in a book is that, oh, we chose Python because it's easier. First of all, I throw that out the window. That's not true. I still stand by this idea that programming languages are all the same. Programming is the skill set. Having said that, a language like Python which is a loosely typed interpreted language, is very, very flexible. And I think it allows a beginning programmer to get away with certain things for the wrong reason. It won't give you an error when you do something that really isn't great programming practice because of the flexibility of the language. So on one hand, you can say, oh, well, that's kind of nice. There's lots of wiggle room, when you're using that tool, which might be nice when you already are, an established computer programmer, you have the skills and stuff. But early on, you kind of want to have constraints that keep you in line so that you gain the programming skills. And reality is you're inconvenienced sometimes when you don't make the most correct decision. Or Python lets you get away with some things, but I certainly wouldn't say it's easier. In fact, frankly, I think in many ways, Python is a more difficult language to work with because they let you do a lot. You won't get an error for things that you actually did wrong from a problem-solving perspective. It let you do the wrong thing because you thought you were doing the right thing, and it won't scream at you, but you'll get the wrong answer. And I think that's not all that conducive with learning. Where C, it'll scream at you all the time. It'd be great. And actually, as you get into programming, and some of you who have had some programming before, one of the biggest skill sets you're going to end up learning is debugging, where you're going to get errors. And typically from a beginning programmer's perspective, you write 3 lines of code and you get 500 errors. Like, well, it's 3 lines of code. Why is there so many errors? Right? You'll realize that it's one error that caused this waterfall of everything else. But reading those errors and interpreting it, almost all of them are the same, are going to be an error that you're going to be prone to, that as soon as you fix it 2 or 3 times, you'll stop doing it. Okay. So by C giving you errors when you do screw up, you're forced into that, let's call it frustrating practice of getting used to debugging your program. So be mentally prepared for a while, that even the simplest programs that you're doing, where you're going to spend 4 hours in your homework, you're going to come to class, you're going to see us solve it in 3 minutes, and you're going to just hate everything about everything. Believe me, a lot of learning took place there, because really what you got used to is reading those error messages, trying to, kind of bang on it, but try to avoid just randomly changing stuff. Because one problem beginning programmers run into is they see, oh, here's a list of errors. I'm not even going to look at them. I'm just going to go back to the code and change something at random. And you might have changed 15, 20 things in a row until finally the moons align and your code runs. But you have no idea why that worked. You just know that it worked. The why is way, way, way more important than the that it worked side of things. Because later on, you'll be much, much better. All right. And that's why I don't grade homework overly difficult. And I give you that self-assessment for you to tell me about the hell you went through to work on this assignment that does nothing. Right. I still have 1,400 errors. You deal with it. That type of thing. And the error might be a missing semicolon, or, a missing curly brace, or too many curly braces, something like that, that you're like, how did I miss that? I often will get the thing where I write code in class and you see it work in class and like, well, I wrote the exact same thing and it doesn't work on my computer. Promise you it's not the exact same thing. It's very close to the exact same thing, but you're missing some little piece. A closing double quote, semicolon, a curly brace. You put a semicolon at the end of a line that it wasn't supposed to be on. Things like that, that I promise you, I made all those errors a couple of minutes ago, right? And through practice and frustration and all that stuff, you finally get it out of your system. I don't even remember the last time I wrote an error. Anytime I put errors in my code in class, it's for learning purposes. I do make errors, by the way. Probably less than you will, but for mental happiness, I'm just going to pretend like anytime I make an error, it was on purpose. So to help you with learning. So in any case, then we have general purpose versus domain specific languages. Almost every language you ever work with is going to be a general purpose language. It's made for solving all sorts of problems, any kind of problem that you can tell a computer what to do. And that falls into that category why I said earlier is, as a human being, if you feel like you have a fighting chance of fully articulating all the steps to solve a certain problem, there's a decent chance you could write a program using a general purpose language to solve it. All right. Domain specific languages, which actually are often written in C. These are languages that you don't even think about, but for instance, like your dishwasher at the house. As long as it's not named Mom or something. Mine was named Tabitha, but now it's named Michael. Oh, I have a machine too, but apparently you have to wash before you. I'm learning all sorts of stuff these days. Yeah, for the washing machine, my wife has created me a packet with an index of every single different piece of clothing has a different protocol. It's actually a good practice for algorithm design, because man, you can't go wrong as long as you follow the steps. But when you look at your dishwasher, you look at your washing machine, whatever, it's got all those buttons on it. There's different settings, right? And probably depending on how expensive or fancy the thing you got was, it might be 3 buttons versus 50 buttons, right? Well, whatever, there's a computer program that's behind the scenes there that frankly is most likely written in C, or a language very, very, very close to C. Those computers are called embedded systems. So they're still computers, but it's usually a kind of a computer on a chip that is not nearly as capable as your laptop is, something like that. But it's good enough to decide, did you push pots and pans, or did you push, I don't know, what's the one for, I don't know, like glasses? I don't know. I always do pots and pans. It seems to get the hottest and clean the best, whatever. But whichever button you pushed, right? So the idea is that that would be a domain specific language where the only functions that have been exposed to for the code is like, if you press pots and pans, do this, do these 4 water cycles in a row, right? Fill up with hot water, spray again, whatever it is, till what finally is everything's clean, right? That would be a general purpose language when it's typically a cut down language that only exposes certain features that's very specific to a certain problem like that. And part of the reason why something like that would use a domain specific language is really for memory consumption. On our normal computers, we typically don't think about this. Something we're going to be talking about here fairly soon, probably maybe this class. It always depends on when I stumble into these things. But kind of the idea of how memory has changed. You know, today our computers have tons and tons and tons of memory in them. So we don't really think about being careful about the kinds of variables we create. Like one of the things we're going to see with C is there's like 5 different ways of storing integers. You can store them as bytes, shorts, ints, longs. You can even store them inside of a variable called a char, and we'll talk about that. But you know, a byte can only hold values between -128 and +127. Whereas a short can hold values between -32,768 and +32,767. Well, realistically, if you're a programmer today, you're always going to store stuff inside. If you are going to store a whole number, you're going to put it in an int, which can hold numbers in the range of -2.1 billion to +2.1 billion. Even if you only need to hold the numbers 1 through 10, you'll still put it in an int because we have so much memory today that we don't have to worry about that. You know, you go to Home Depot and the gigantic bucket is on sale, even though you're only going to put 1 pair of shoes in there. It's like, well, the giant bucket's cheaper than the smaller one. So you're going to buy the giant bucket and you only fill it up, 2% of the way. The way we think about computer programming today kind of follows that because we have tools available to us where we don't have to think about that kind of stuff too much. It's like, oh, I need to hold a number. No problem. I put that in an int. Even though an int is that giant bucket that's taking up more memory than it needs to take up in your computer. But now when you go over to these domain specific things like our dishwasher, well, it could be a major difference whether they have to buy the cheapest computer on a chip versus the one that has just a little bit more memory. You know, when you look across 1 million different units that they have to create for that dishwasher, that could be real money difference, even though it might only be like 8 cents difference per computer, right? So the idea is by using a domain specific language, the ultimate program is a lot tinier. Because when we write a language, a program in C or C++, like hello world, that program did not require that many bells and whistles. I mean, we probably believe we didn't really stress the number of features that the C programming language gives to us to write that hello world program, right? We kind of just did one little magic trick, print something, okay? But when we compiled it, it brought into consideration the entire C language, the standard library that's part of the C language. And because of that, our actual executable was, fatter, took up more space than it really needed to because it had capabilities brought into it that we didn't take advantage of. So ultimately it ended up being, I don't know, let's say it was 4 kilobytes in size was our executable maybe, when really it only needed to be like, a third of 1 kilobyte. But we didn't care because the computer has umpteen gigabytes of RAM. So who cares? And we'll know what that means in here. So if you have heard things like gigabytes and megabytes and things like that, and those are just things, you're going to know a lot about those here pretty soon. Go ahead.
You said before, like in modern programming,
Yeah, or long if it doesn't fit.
Would there be any advantage for like
Memory footprint? Yeah, that's it. And really, most of our modern day compilers, I mentioned last time that compilers are very difficult to write, and that's why we actually don't have that many new compiled languages that come out. But they try to make a bad programmer look like a better programmer. So it has some magic tricks in it where when it's analyzing your high level code, it will sometimes be able to notice that, oh, you've used an int here where you actually only need 8 bits of memory to do what you're doing with it. So I'll behind the scenes pretend like you said byte and put it in the right kind of assembly language, use the right size register on the CPU, the one that can hold 8 bits instead of the one that can hold 32 bits, something like that. But yeah, I would say every now and then the answer to your question might be a little bit of speed, but 99% of the time
It's not a.
it's memory footprint. Yeah. And because today we abuse our computers to say, look, this is your problem. You know, our computers now, you know, you have, you know, even the cheap ones have 4 cores. They have quad core processors. You know, they have, you know, a zillion different places to store things on the actual processor. Plus your system memory in your computers, even if you buy a cheap laptop today, has at least 8 gigabytes, probably 16 gigabytes of memory. It's not uncommon for people to have computers today with 32 or even 64 gigabytes of memory. I bet you any of you who have a gaming PC at home or in your dorm room have at least 16, probably 32 gigabytes of memory. And then you have, you know, some graphics card in there that probably cost half of what the whole, well, probably maybe more than half of what the whole computer costs. Punchline being that things that we used to have to worry about as computer programmers back in like the 80s, we don't really have to worry about anymore. And actually, I'll just kind of give you a quick little story associated with that. So out of curiosity, who in here has at least 16 gigabytes of memory in their computer, in one of their computers? If you don't know what I'm talking about with gigabytes and stuff, it's not a problem. I'm going to teach you about it. But what about at least 32 gigabytes? 64? Oh, we have a 128 in here? 128 is the highest you have. You don't have 256. You have 128? Yeah. Yeah, we had a student last semester who had 128 in theirs. And what percent of that memory do you think you ever use? Unless you're doing something crazy, you're running, yeah. I bet you at most you're probably ever using no more than 8 gigabytes of that memory. Yeah, but I mean it's bragging rights, right? You know, it's like when you go out and buy the pair of sneakers that was $700 as opposed to going into Payless. You know, it's like, look, they're going to wear out at the same time, but the $700 sneakers you don't even put on, right? You put them in display cases. It didn't make sense. But I did the same stuff when I was younger.
Have you seen that video?
Oh, and they took Payless shoes and they put them in fancy boxes, and all these people they were buying like $600-700 shoes for a $19 shoe. They were paying $600 or $700 just because it was in a box that had a certain name on it, but they were Payless shoes.
And they pretended to know they were super great.
Right. I saw a similar thing several years ago with like a fancy restaurant where they took like TV dinners and cooked them up and then, prettied them up on the plate, but it's the same food from your, banquet $1.99 TV dinner, and they served it as some sort of, expensive, $69, steak special or something like that. And, they were interviewing these people like, oh yeah, it really had, just a good blend of flavors. And I really felt like, the garlic just came, they're just critiquing this like it was Iron Chef. But then you always have this one person that knows. It's like, yeah, I wouldn't know. That's garbage. What did you cook that in a microwave? Yeah, and in the back, they have they're showing the dirty microwave they made it. So, I mean, that's just how humans are, right? We like status symbols and things like that, but at the end of the day, they all do the same thing. I'm not a car guy, but I have a Tesla because I'm a tech guy. But I mean, a cheap Honda will get me to work, right? You don't need a Tesla. So I don't know, it's all a status symbol, stupid stuff. But in any case, today we have a lot of memory available to us. Now, the reason I say that the idea has changed is, and I'm sure we'll bump into it again here, but I'm going to go ahead and write it in. We'll write it in this slide right here, because it tells us a story. The cost of memory. So I'm saying memory used to be really, really, really expensive. All right, so since some of you obviously have gaming machines, you're familiar with the cost of memory. How much is a 16 gigabyte memory stick? Okay, probably even less than that, but 50, let's go 50. Okay, we can even go 70 or 80. It's still going to prove the point. So let's say 16 gigabytes of RAM.
$6, $3.12 per gig. And then-
Okay, yeah. So that's good. All right, so this was $50. And you said this was $3 and what per gig? $3.12 per gigabyte. Okay, and that's in 2022. All right. So now let's roll back the clock to 1996. How many of you were alive in 1996? All right. So in 1996, I bought an 8 megabyte memory chip. Okay. Before I go any further, I'm going to write another little thing here because we're just call this bytes, etc. Because one of the goals in here, and I promise you it's important for computer programming, is we need to know what all those words mean instead of just letting them fly by. And I'll prove that to you here in a second. All right, so we have a bit. What's a bit? Everybody know what a bit is? When I say something is 8 bits, what do I have? A 0 or a 1. That's what a bit is. So we have a second column here where we have a byte, which is 8 bits. That's how we convert from the left column to the right column. Okay. So over on the bit side, we have something called a kilobit with a small b. This is the kicker, the small b. Whether the K is capitalized or not is less significant, but if it's a small b, that's kilobit. So how many bits are in a kilobit? Is that 1,000? Okay. That's the common wrong answer. It's also the best buy answer. 1,024 bits. You'll see why. 1,024 is a power of 2. It's a power of 2. Digital logic, zeros and ones. There's an on-off position. We have 2. Everything in computers, by our modern day computers, is going to be something related to base 2. Okay. You start getting into quantum computers, we actually have 3 states. Because there's a spin state. Quantum computers is actually fascinating. I think they'll talk about it in 175 a little bit, but at some point, you know, if you corner me in the cafeteria or something, we can talk about quantum stuff. It's fascinating. I went through, I got certified in all 3 levels of the quantum stuff. And man, that makes you like question reality. It's awesome. It is weird. I'll probably get off on that tangent at some point. So you might even hear it in here, but whatever. All right. So a kilobit is 1,024 bits. A megabit is 1,024 kilobits. A gigabit is 1,024 megabits. And we'll just go up to terabit, even though nobody uses that right now. 1,024 gigabits. All right. So once you know that 1,024 number, that whole left-hand chart is pretty easy to just create, right? Bytes, we have something called a kilobyte with a big B. When you see a big B, that means byte. So that's going to be 1,024 bytes. A megabyte is equal to 1,024 kilobytes. A gigabyte is equal to 1,024 megabytes. A terabyte is equal to 1,024 gigabytes. Leave it at that. Kilobyte, megabyte, kilobyte, megabyte, gigabyte. Okay. Makes sense? So that's our breakdown. Not that hard once we know that 1,024 number. So as long as we can know a bit is 0 and 1 and a byte is 8 of those, we can translate between these 2 columns and then that 1,024 number to go up and down. Okay. And the reason I point this out, so how many of you have internet at home? Most of you. How many of you know what the speed of your internet is? What's the speed of our internet?
50 down, 10 up.
Okay, so call home internet. Who's your provider? AT&T?
Spectrum.
Man, you got crappy internet. You got the free one?
No.
Are you out in the boonies?
No, we're
I
like.
didn't even know they sold that low. We'll go with it. It's fine. Okay, so yeah. So he says he has 50. He said 50 down and what up? 10 up. All right. Notice he's conveniently left off that 50 what off that. So typically home-based internet is what's called asynchronous internet. Your download speed is much faster than your upload speed. And the reason for that is your upload speed is somebody else's download speed. So they don't want you to run servers out of your house, right? So a slower upload speed, we typically will use our upload speed for like email attachments or, making a tiny request to like, take me to Microsoft.com, those kind of things. Very, very tiny, send instantly. You don't need a fast upload to accomplish that. Okay, so it's 50 what down? Megabits. All right, so if you look at the things, it'll be megabits per second. But what do the commercials say? Commercials say, oh, it's 50 meg. Sounds better. Okay. You said yours is even worse. What's yours?
So ours, we finally, and Manny, we finally got fiber, which is awesome. So it's not a millisecond thing, but really expensive. So we're like in the second lowest tier, it's really expensive, 25 down and 12 up.
And you're on fiber. So who's your provider?
CSC200. So it's a local.
Is it a phone company?
Yep.
Okay. So they probably have fiber down, but you're actually on a DSL circuit.
No, we have fiber to the home.
Are they paying you for that speed?
No, it's $70 a month.
Oh my gosh. Oh my gosh. So typically in the Milwaukee area, your budget pleaser spectrum is about 200 megabits down, and probably 15 up, maybe something like that. They have a premium one, I think is 400 down and probably like 30 or 40 up. And then they do have a gigabit internet from Spectrum. AT&T, which does have slower based internet because it's based on a different technology. It's not that AT&T sucks compared to Spectrum. It's just Spectrum's using cable modem technology. AT&T until more recently is using what's called DSL stuff. So your speed is very much related to how close you are to, it used to be the home telephone office, but now it's close, your distance to something called a DSLAM, which is like a repeater. They put them in neighborhoods to be able to offer DSL farther out. But now the phone companies, AT&T and Verizon are doing it. They have fiber optic cable going actually to their destinations. They're upgrading the old telephone system because most of our landline telephone system anymore is based on top of just old twisted pair. It's called POTS, plain old telephone service, right? So historically, we would use dial-up, right? You get one of those modems, and you'd use dial-up to connect up to the thing. And how many of you have ever seen them or used a modem? They use a modem? Anyone see them in a museum?
I remember one.
Yeah. You remember the sound they make? You know, that's dial-up. Yep. Yeah. Yeah. So I think my first internet connection was 300 baud, which is 300 bits per second. The fastest dial-up internet was what's called 56K. So that was 56 kilobits per second down, and it was 33.6 kilobits per second up. Slow by today's standards, but used to be turbo. That used to be like people were envious if you were able to get 56K at home. All right. But in any case, now that the phone companies are able to get fiber and some of they've had it in Milwaukee for a while. They're just now getting the fiber up in Mequon. Once you have that, you'll be able to get gigabit internet from AT&T. But the real reality here is that you're probably not using internet that's fast, that much of your internet, kind of similar to the memory example here, and we'll explain that here in a second. So typically cheap spectrum internet in the Milwaukee area is 200 megabits down by, I don't know, let's just call it 15 megabits up. The up doesn't really matter. We're just going to call this 200 megabit internet. So the question is that a lot of people translate this as, oh, I get 200 megabytes per second. It's not. You have to take the 200, you have to divide it by 8. So your maximum download speed, your maximum theoretical download speed is 25 megabytes per second. So I took that 200, I divided it by 8 to jump to the byte column. That makes sense? Okay. Now, when I say it's 25 megabytes per second, theoretical maximum speed, why wouldn't you always get 25 megabytes per second? What do you think? Yeah, but you want it. You're paying for it. You're paying for your 200 megabits per second. You should get your 200 megabits per second. All right.
Is it because when there's more people using it and it's slower, especially without fiber?
Okay, yeah, I would remove the especially without fiber thing, but why is it slower and more people are using it? I actually told you the answer a couple minutes ago. You maybe just didn't realize I said the answer. Your download speed is their upload speed. So let's assume, we'll give an extreme thing. Let's say you got some like old school guy on the corner still using dial-up, right? You know, he robbed a museum. I actually probably still have one of my 56K modems in a box in my basement. It's probably labeled tax documents. I might not be kidding. Because I was in charge of unpacking 17 years ago, and you know, my wife has taught me there's an onion technique. You do a little bit at a time, so I may be 5% done, something like that. But let's say that there's a guy at the corner. He's running your, it's comic books, and you can download comic books from his server that he's running off of his 56K modem. Now you have gigabit internet, super fast, crazy turbo internet. Even though you're capable of downloading at 1,024 megabits or 128 megabytes per second, the fastest you're going to get is 33.6, which is his upload speed. Because that's all he can only hand it to you that fast, regardless of what you're capable of pulling down, right? Now, so who is going to have, let's say we have this 200 megabit per second, 25 megabytes per second internet. The companies that will have that kind of bandwidth are going to be your big boys, like Google, Microsoft, things like that. So when you download things from like very established companies, they have a big upload pipe, but you're still going to be limited. If there's 10 people operating, downloading currently off of, let's call it 10 megabytes per second, you're only going to be able to get 1 megabyte per second pulling from it because you're sharing that upload bandwidth. Okay. But now realistically, most of the time we're not downloading these gigantic files. Most of the time you're playing your video games, it's sending these little tiny packets of information, less than 1 kilobyte of information. Is just sending it often. And a couple minutes ago, he mentioned this thing called ping. Gamers care way more about ping than bandwidth, because ping says, what's the time it takes to send something to the server and receive a response? Higher the number, the worse it is, right? So when you get like 3,000 ping, okay, that's a 3-second delay. The only person that I know that wouldn't impact in any of those first-person shooters is me. Because man, I'm terrible at them. When I play with students, they usually have to, when I run out of the bullets, they have to kill me so I get a fresh gun. I'm not very good at going and getting a new one. I miss it. And then they screw with me. They come up and they put like little turrets right in front of me, and I don't run around fast enough, and I don't hide behind they're jerks. it's, it's bad. And then of course I just fail them because it's, you know, they had it coming. Nobody would convict me. So, but faster ping, the better. There's a point where it probably doesn't make a real difference. If you have a 4 millisecond ping versus a 9 millisecond ping, I mean, unless you're operating at this top level echelon of, you know, pro gamer type stuff, that's not going to make some, you know, any sort of real difference. But the reality is, and the important part of that is, to do those video games, you don't need any more than like probably 5 megabit per second internet. Because the need of those real-time video games is not bandwidth size. It's speed of return around message. All your graphics and crap that's being shown, that's all installed locally on your computer. That's why when you installed your latest, greatest video game, it took 15 minutes and then downloaded for a day, right? You know, the upload or the update or whatever. Okay. So kind of keep that in mind, that faster internet doesn't necessarily mean better internet. Why might somebody get 400 megabit per second internet, the upgraded version of Spectrum, rather than 200 megabit per second? Why? Why would they want 400 megabit over 200 megabit if they really, based on their usage patterns, they really actually only need no more than 30 megabit to, like, you know, I think it's 35 megabit per second allows you to stream in 4K from Netflix. Go ahead. Yeah, more people in the house. So it's not that an individual person needs more than 35 megabits per second for whatever task they're currently doing. But if you have more people in the house that are all using the internet for different things, then you got to think about all your extra devices, your Alexas and your, you know, we have YouTube TV and all our cell phones are on it and it's checking your emails. You have all these smart devices around the house that are using part of your bandwidth up. Realistically, 200 megabits per second is probably fine for most people. You know, and even, you know, if you had 50 megabit per second internet, still, that's fine for most people. So it's not really a problem, but, you know, it's a bragging thing, just like his 128 gigs of RAM. You know, doesn't matter whether he uses it, he has it. So the people with like the V12 engines in their car, you know, it's like, oh yeah, it's got 4 million horsepower. You know, I get 1 mile per tank of gas. They basically live at the gas station, right? All right, so that's kind of the punchline there. But, you know, keep in mind with these bits and bytes type things, it's often the situation that will, I mean, I think it's criminal, but like these TV commercials and stuff try to take advantage of your ignorance, because most people don't know that, right? I mean, we're even tech geeks in here, and the best we came up with was 1,000, right? He didn't even want to give me the thing that was after the 50. Well, I got 50 something. You know, right? And he was 1,000. 1,000 is not bad. You know, at least you're getting a rough estimate, right? You're in the ballpark. But it is 1,000 and yeah. Right. Yeah, in math, you'd be right. But just specifically with computers, it is 1,024 because it's a power of 2. So back to this example here. In of RAM in 1996. How much do you think I paid for 8 megabytes? So remember, if we're going to convert, so we need to take 8 divided by 1,024. So if we want to have the conversion, this is 16 gigabytes. This is 0.0078 gigabytes is what I bought in 1996. All right. What do you think I paid for 8 megabytes of RAM? Go ahead. 500? More. Go ahead. That was about $1,000. That was $1,000. Now, here's the kicker. This is after memory had already started coming down in price. It used to be more expensive. Okay, so $1,000. So this was $3.12 per gigabyte, right? So $1,000. If I take 1,000 divided by 8, that gets me $125 per megabyte. Multiply by 1,024. That's right, the right math. That's $128,000 for a gigabyte. Times 128, he has, in 1996 dollars, he has $16,384,000 worth of RAM. Yeah, you can almost afford, bench seats at the Packers. All right, so this is after memory had already come down in price. Now, keep in mind that in 1996, the complexity of our computer programs was different than the complexity of our programs are today. Processors were slower, we had less RAM, so we weren't able to push our computers as far as we can today. And we also didn't have the time with all this innovation of human beings coming up with better, interesting ways of writing software, right? I mean, when you think about your smartphones, whether you're an Android or an iPhone person, really Apple's App Store is what really started the idea of the smartphone apps. You know, Apple had some interesting apps on the phone initially, but the App Store wasn't there for the first year. When they released the App Store, allowing zillions of developers to start writing smartphone applications, that's where all these different creative juices start flowing and people come up with interesting apps like the Fart app or Angry Birds. Whatever, you think about some of the successful applications that have been out there that maybe Apple wouldn't have thought of or something like that. But sometimes, the faster the processors, the more the memory, the better connected we are with the speed of internet connections and latency and things like that, the more we might be able to be capable of as human beings writing software to do something. Okay. So what did we come up with? So this was $1,000. So what was it? 128,000. 128,000 per gigabyte. Cheap. But nobody had a gigabyte of memory back then, right? I suppose maybe some, supercomputer type place that had, some special custom hardware made for them. Maybe they had a gigabyte of memory for some scientific purpose or something like that. But people did not have that much memory. 16 megabytes of memory back then was considered a lot. 16 megabytes then was probably equal to our 64 megabytes today, or 64 gigabytes today. You were at that level of cool. Okay. I mean, you weren't just like, not even talking to people with 128 gigabytes. Like, look, let's just start off with you're beneath me. Whatever you have, it's not enough. Is this the starting point? All right. So anyways, we have this whole byte chart. So this is something you will want to memorize. This is one thing I may ask you to do. In fact, all my exams that you'll ever have with me in any class, because you're going to have me for several classes during your 4 years. I always ask at least one conversion question on the exam. So it'll either be a question like this, like how many gigabytes per second is 225,000 kilobits per second, something like that. Ask you to convert between some of these things. Or I ask you to do number-based conversion. All right, well, so like convert some number from binary to hexadecimal, that kind of stuff. We're going to talk about that here. Well, let's talk about it now. Well, what are we doing on time? 11:09. Let's finish this chart a little bit. All right, so I'm going to say roughly, what time are we at here? 11:20. So roughly 1968. I'm going to throw an ish on there that way nobody screams at me. All right, we had a language called C. And C was strongly typed compiled and procedural as opposed to object oriented. I think that was like the last thing on here. Object oriented versus procedural. Almost all of our modern languages are object oriented languages, and we'll talk about what that means when we get to it. But beginning programming, doesn't matter whether the language is object oriented or procedural, our programs are going to look the same because we're not using objects yet. We're doing everything in like starter beginning programmer type stuff. All right, so we can just go ahead and make the assumption that new languages came out as like, oh, the old language was good, but here were the problems with it, and now we're going to fix it. All right, so early day problems where our program started getting more and more complex, and we started finding the need for objects. And later on, when we introduce objects, we'll talk about what that means. So we had C++. And we had Objective-C. This is the old Microsoft versus Apple war. So Apple, Microsoft, they didn't like each other. So Microsoft went C++, so Apple went somebody else, right? So they got behind an open source project called Objective-C. Both of these are object-oriented versions of the C programming language. So they are strongly, strongly, strongly influenced by C. In fact, very often, if you looked at a program written in either of these languages, you'd have to hunt around to find the differences between either of those languages and C, unless they're specifically using objects. It's the same syntax. Even our most modern languages use C syntax for most of their stuff. Okay. Now, we just stay on the Mac side for a couple of minutes. And really, I'm going to advertise it as the Mac side. This is the PC side. Yeah, so Apple's always had really great naming conventions. So, they pushed for an updated version of Objective-C to get to Objective-C 2.0. And the guy that came after C++ on this side was a language called Java. Okay. Super famous lawsuit here. Anybody know who created Java? You can give me the modern company or the company it used to be. Modern company is Oracle. Who did Oracle buy that actually created Java? It's Sun Microsystems. There's a company called Sun Microsystems. Oracle eventually bought them. Sun Microsystems, when they're on their stock market ticker symbol, was Java. Java was their stock symbol. The fun story there is Microsoft stole Java. And the thing is, it's not even demonizing Microsoft. All these big companies, what they do, they steal stuff because it's cheaper for them to take it, have it today, settle outside of court, and move on with life. I mean, I don't even know if I disagree with it. I mean, it doesn't seem overly ethical, but if you're, some kid who writes something in your basement, you're in grandma's basement, and you come up with this cool idea that you'd never be able to market and sell yourself, and all of a sudden Microsoft steals it, you sue them, it doesn't even go to court because they just say, hey, here's 10 million bucks, go away. It's like pretty solid Wednesday, right? Now maybe you would have made 10 million or more off of it, but in most cases, probably not, right? Huh? Yeah, people do that. Yeah. I mean, a lot of times as we get closer to it, I get students involved in our CU launch entrepreneurial competition here. to create businesses, because it's, I mean, almost everybody, you know, gets at least $1,000 in seed money if you get involved in it. But the idea is that one of the main things when you're starting a company is to think about what your exit strategy, and typically part of your exit strategy is, who are we going to sell the company to? Who would this be valuable for that will ultimately buy it? That type of thing. All right, so we came out with Java. Microsoft, let's call it, stole Java. They had their own virtual machine for it. We'll talk about Java more later, but I'm not going to get into the depths of it right now. But so you had Sun Microsystems version of Java, and then you had Microsoft's version of Java, and they were, let's just call them the same. So the difference is that Sun Microsystem wasn't that kid programming out of his mom's or grandma's basement. You know, this is a big, publicly traded, multi-million dollar company. Maybe not quite Microsoft size, but definitely one of the bigger kids on the playground. So they took Microsoft to court. They won the lawsuit. Microsoft had to cease and desist. And they came out with a brand new language called C#. I was at the, this was at University of Illinois in Urbana-Champaign. Was it maybe year 2000-ish? It was an ACM conference where Microsoft was there, and it was when they first announced the C# language. And everybody goes to the Microsoft things because they hand out the best free stuff. You know, the other vendors, they're giving bouncy balls and stuff like that. Microsoft, they were handing out box sets of Visual Studio 6.0, which is like a $400 piece of software. You know, and of course we had all already pirated it, right? So, you know, that's $400, wow, probably $350 because you want to move it quick, right? You know, you sell it to somebody, whatever, but you know, obviously don't do that. I've learned my lesson. So in any case, they announced C#, this brand new language that they built from the ground up, yada, 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 yada. Different syntax, but you know what? They basically describe Java. No problem. It's still, they technically made enough syntax changes that it was no longer a direct competitor. And in many ways, C# has some technology improvements over Java that were good, that Java has gone back and incorporated into their future versions. So, I mean, today, if you were to go out and get a job as a software engineer, I would say your most popular languages that you'd likely be programming in is probably a fairly tight race between Java and C#, Java and .NET. Probably Java is the most popular today, and that has more to do with Java's this thing called a cross-platform tool, so you can write the software once and it'll run on Mac and PC and Linux all at the same time. But C# super popular. C is still very popular for a lot of these old embedded systems and stuff. And then Python is becoming more and more popular from a machine learning, artificial intelligence side of things. All right, so this was kind of on this side of things, and this is really where we've ended up here on the PC side. And this sat for a long time, and I think it was around maybe 2015-ish. It might have been a little longer than that because you know, this time goes by quicker, but finally Apple came out with a language called Swift. Okay, and by the way, all of these languages are compiled. These are all compiled, strongly typed languages. Now the funny thing is if you were an iPhone programmer, which that was the place to make money as a independent contract or independent programmer early on. So you had to go and learn Objective-C to write the iPhone apps and stuff, and you could just make bank in the early days of the iPhone. I had 4 apps on the iPhone App Store day one that the App Store went live. I'd gone out to the Worldwide Developer Conference. I've talked to some of you outside of class. I used to run software companies. I sold 5 companies a while ago. Then I retired and I needed health insurance. So now I teach programming. So, so that's the, because, they charge a lot for health insurance when you're fat. It's terrible, but group health insurance, it's included in my salary. It's great. But in any case, so I had 2 different dice rollers, like Dungeons and Dragons dice rollers. And then I had the pro version, which was $1.99. I had the normal version, which was 99 cents. And then I had the 2 first real-time stock quote applications on the market. One was called Quotes RT, the other one was called Portfolio RT. And later on, I had a zillion other apps, but those were live on the store day one. And what was interesting is, first of all, Apple people are usually more affluent, especially back then. It was because the phone was really expensive. But you also had like grandmas and stuff just buying every app that was on the App Store. It was like stupid. And the funny backstory, is that the 99 cent dice roller, how much do you think I made off that app in 6 months? Well, I will end class $3 million. I will end class with that. But in any case, they came out with this Swift language years later. Apple people were not complaining about Objective-C. Swift looks a lot like Java, which is the native language for writing Android applications. Yeah. So Apple came out with Swift to try to get Android developers to come over to the dark side. Kind of the punchline. All right, we'll pick up from there on Tuesday, right?